talked about differential equations and separation of variables, right? To solve differential equations. We have already talked about this. Yes. Thank you. Because you're live. And that's if you can separate them and solve them, then you can come up with a general solution and then a particular solution, right? However, not all.
I didn't mean.
Not all differential equations are solvable. Meaning you can't separate, and not all things are integrable. Okay, which means you can't take the integral of it. Okay, so we have to come up with a numerical method, or somebody came up with a numerical method, namely Euler came up with this method in order to help us solve differential equations, or at least give us an estimate of what the function value might be if we know the slope and at a point, and if it's reasonably close. Okay, so we're going to talk about Euler's method. Like I said, it's about this guy named Euler. He lived a long time ago, clearly. It's a beautiful picture of him. Oh my God.
Where's he from?
Europe. I should know that, right? He made a large contribution to math, but he was almost blind. So that was like a hardship of his. And that is him. He's a famous guy. He originated some of our famous notations that we use, like function notation. So we can thank him for the f of x notation. And I like this because it tells you what x is. You know, if you know f of 2, that shows you what x is. Also, he helped us find out what, or at least name the natural base. It was occurring all the time. And we said, oh, that's a number we should probably pay attention to, right? And I. And I. In our favorite summation notation. Right? And finite change. Famous guy. All right. Sometimes we can approximate a function value if we're, like I alluded to a moment ago, when you're starting at a given point, you know the slope. Okay? So this is Euler's method. So what do? You begin at the initial condition. This is the point that they give you, right? They're going to give you an xy point. You find the slope of that point because you're given the derivative. And to find the slope of that point, just like we'll find the slope, you'll just plug in the x and the y. Find the slope of that point. And then we increase x by a small amount, meaning, what would you consider small?
0.1.
0.1, but sometimes it can be 0.5. It could be, however close you think is reasonable. And then we use the slope to find out an approximation for what the change in y is going to be. Because we already calculated the slope, didn't we? And so we take into account here that the slope is dy dx, and then multiply it by a dx, and that will give us a dy. And it gives us a new point, which is x plus delta x and y plus delta y. So you're traveling along a little tangent line. And then however many iterations you want to do. Okay, so let's go through the process. Let's see what we got. There's my curve. Really. That's my tangent, points of tangent, see, right? And then what am I going over? A little bit of delta x. And then I'm going to use the slope to help us go up a dy. Okay? And so is that an underestimation, that new point? Because it's not on the curve, is it? No. So if it's concave up, it'll be an underestimation. But then you can repeat the process and find the slope at that new point using the same derivative. I'll keep going here, hang on. Yeah, we want one that practice of easy to solve. So here we go, the initial value is 0, 1, and the slope is, or the derivative is 2x. So what's my initial point? 0, 1, and let's say we make a delta x, which means the change in x, 0.5. So I usually set up a table where this is the number of iterations. And this is our original point, right? So that's 0. And then I find, obviously, one point. The derivative there, which is what? That's 0, 1. You plug in this point, right? At 0. Do we follow what I'm doing? Okay, and then we figure out what the change in y is by multiplying it by the slope. When I say it by the slope, I'm talking about delta x. What is delta x in this case? 0.5. So 0.5 times 0 is 0. So there, even though we have a change in x, there is no change in y. So we're just going horizontally to the new point, which would be, we're adding 0.5 to the x, and we're adding nothing to the y, so our new point's going to be 0.51. Okay, and then this is our new point, 0.51, and then I'm going to find the slope at this point. What is the slope at this point? 1/2 times 2, which is 1. Of course, then you do that, that's the new point. And then the slope is 1. Now I'm going to take this slope and multiply it times the change in x, which is always 0.5. So it's going to be 0.5. And so I'm going to take the y and I'm going to add 0.5 to it because that's the new estimate for the change in y. So y is going to go from 1 to 1.5. New point is 1.5. And now what am I going to do? Use this point here to calculate the slope, which is now 2. And I'm going to now figure out what my approximate delta y is by taking 2 and multiplying it by delta x, which is 0.5. So my change in y is 1. And my new point then is going to be, this number is now going to be 1.5 plus 1, which is 2.5. So my new point is going to be, I added 0.5 to this, so it's now 1.5, 2.5. Do you see how I'm almost mirroring? What's the antiderivative of this? X squared. Does it look like it might be kind of like x squared? What we're doing is, through these iterations, is we are approximating the curve. We are approximating the particular solution that passes through the point 0, 1. The exact solution, like I said, the antiderivative is x squared, right? If we separate it and integrate it, we get x squared plus c. We can solve for c because we have an initial condition, 0, 1. And so c we know is 1, right? We plug that in. X squared plus 1, and if you draw that, you see how what we did with Euler's method by just using an x step and approximating using the slope at each new point that we came to, we're mirroring the rate of change. It's not perfect, but it's starting to look like the curve, right? Even though it's an underestimation. If we get close enough, instead of 0.5, you think it gets even better? It's closer to the curve. And you might say, well, why on earth would we do this? Because we know how to integrate this one. We can find the particular solution, right? Like I said, there are curves you can't integrate, separate and integrate. And that's called Euler's method. Obviously, I always steal my own thunder, you know? It gets less accurate the further away you get from the curve. So it's really accurate here, but the further you get away, the estimate gets worse. I think that makes sense. I haven't done slope fields with you yet. We have to change our mode. So if we go to mode, we're in function mode right now. What mode do you suspect we're going to choose? I challenge you to do that. We won't do it. Okay, so we're going to go to y equals, right? Take these things, and then we're going to go to y equals. Now, when you go to y equals, it looks a little bit different, doesn't it? Now, our slope has a y in it on this side, right? So it's like implicitly defined. So I have to, this calculator, if you see, has y1, y2, you know, goes all the way down. We have to, if we're putting in the y1 line, you have to put, this is y1 prime equals, you see how your calculator says y1 prime? And then you're going to put in 0.001 times, and you have to physically type y1 because that's my solution, right? y1 prime goes with y1 times 100 minus y1. You got it? You already know. And anytime you see an x in your expression, you notice that it's already a function of t in there, so wherever you see x, you've got to use t. All right. That's just moving up the screen so you can see it more. Now let's go to our window. The window looks a little bit different, doesn't it? So help yourselves to my window settings. Now I never mess with M curves. This is a differential tolerance, and this is field resolution. I just leave those alone. Hopefully yours are set like that automatically, are they? Yeah, I leave mine alone, I don't touch those. All right, everybody got their windows set? Not quite. Okay. Yes, we're ready now? Okay, and then, like I said, macro I never mess with those values. All right, now we're going to go graph, and then this is going to be the aha moment. Let's see. Woo, nice. You got a slope field. That's pretty nice. Does it match mine?
How do you know when to set the window to?
Well, I kind of know what the solution is ahead of time. You know what I mean? So, you know, you'll get a feel for it once we do some more. All right, while the calculator is still displaying on the graph, let's do this. Diamond such that bar. And change the solution method to
Euler.
Euler's method, okay? Got it? Now, there were several solution methods, right? One was Euler's.
Okay.
That's Euler's cut up? Oh, okay, okay. And now let's go diamond y equals, so we can go to set our initial condition, right? So that's what I1 means. That's an initial condition, right? That's the initial y value, which is 10. And let's go to the window and change our t step to 0.2. The t step is bigger, the graph is faster. The smaller the graph is more accurate, so there's a trade-off. So what was it before we changed it? Well, I mean, right, the very first thing you changed, what was it before?
The solutions.
You don't remember when you changed it? I don't remember.
I thought it was 0.2 already.
0.1, so this is bigger, so what does that mean? It's gonna be faster, but less accurate. All right, now we're gonna go diamond graph. What do you see? What's going on? Yours should eventually look like this. Is it slow? Yeah. Okay, so can you tell me what kind of graph this is? It's a logistic.
Okay.
Very nice. We haven't figured out yet how to solve a logistic differential equation, but that'll be next time. Okay, but that is your particular solution, passing through the point 0, 10. Okay? And then it graphed it using the Euler's method, which is really kind of cool. Let's plot a different one with a different initial value. Let's go F8. And either move the cursor to enter another. You want to change your initial condition? Why don't we do something that's above this line? Or you just make your own condition, that's fine.
One, like just spits it out.
There you go. So what happens when your point is above the graph? Right, it's like a population of zombie rabbits, right, on an island. So when somebody decides that I'm going to drop off a whole bunch of zombie rabbits, what happens to the population? It decreases to what the island's carrying capacity is, right? But if you don't have a lot of them, it'll increase to what the island's carrying capacity is. Do you see what I'm saying? So that's kind of what's going on. Pretty cool, huh? All right, so let's go to y equals again, and let's change our differential equation to the one that we did a minute ago. And remember, when you see x, what do you have to put instead of x? T. So this is going to be 2t. And then in y initial, you're going to put in 1. Diamond y equals, and then obviously I reminded you of that. And then we're going to change the window. Now we want the window smaller, right? Because we know this is x squared equals 1. And so that huge window that we got a minute ago is not going to be helpful. So these settings will be helpful. You notice that this change to Euler step? So just leave that alone, though. Everybody got your window changed?
What was the arcade solution?
It's another numerical method to solve differential equations, but you learn that in college. And there's a modified Euler's method as well that they teach you. So you learn separation of variables, which we've done, and then you learn how to solve some first order, differential equations, and then they teach you some other numerical methods. And one is the modified Euler's, and the other one is Differential, which is a little bit more involved. So if you take differential equations in college, I recommend it. It's one of my favorite classes. But it's just a more difficult, system where you reiterate. Sometimes you do averages of, slopes. Like you'll take a point and you'll go to the next point and you'll average them. I think that's the modified Euler's. But anyway, all right, so did everybody get their window changed? And did you get a chance to look at what happens to you? You have to do this again. You get? Let's change the fields to off. And let's go to the graph. And there's the solution. Now, what did we do when we turned the fields off? We got rid of this, the slope field part. So that's our graph that we knew and loved, right? Now you can use F3 trace. What were the other, do you remember the points that we had? We went in increments of 0.5, so it was like 1 to 1.5 to 2 to 2.5, right? So if you trace along this curve, you should get the very points that we did. Or you can look at the table, and you can have edit where our table starts. You go start at 0 and put it in increments of 0.5. Let's do that. Diamond table set, and we'll start at 0 and change to the table will make 0.5. Enter, enter. And then go second table to look at it. And you see our increments, and those were the values that we got. So the calculator will actually do this for you. It's pretty cool. Now, what if you want to build these slope fields again? You would do diamond, such that, and turn the fields back on. How do you do that? Let's see what the slope fields look like. Cool, huh? If you're following the slopes. What's durable? That's the direction field that would like vector field. All right, you go to the table and you see that you got the exact same points that we had earlier, right? Using Euler's method, using the slope to go along. Yeah, so you don't have to know that. All right, so let's do some examples by hand. Because a lot of times what happens is that this is on the non-calculated section, because they want to make sure you understand the process. Yes? Okay. Now, you might want a separate sheet of paper, just because, I make my table reasonably big. Everybody got your sheet? So when a question says Euler's method, the very first thing I set up is a table, and I make it x, y, which is my point that I'm starting out at. And then I always do what delta x is. And then I say, okay, what is dy dx at this point? And then I say, well, delta y is approximately dy dx times delta x, right? We're approximating that. And then lastly, I say, my final point is x plus delta x, comma y plus delta y. All right, so this problem says, use Euler's method with delta x equal to 0.5 to approximate the function value 3.5, where f satisfies the initial value problem, f prime of x equals x, and f of 2 equals 2. So where are we starting? 2, 2. So that's what we're going to put right here. Now we have to go to 3.5, right? So we're going to have a couple of iterations if we're only stepping in 0.5 in the x direction. So obviously delta x will always be 0.5, you know? So what is, and my slope dy dx is equal to x. I'm here to you to start off simply, right? So dy dx equals x. So what is the slope at 2, 2? It's 2. And then we're going to use the slope and delta x to approximate what our change in y is going to be, which would be 1. And so the new point is going to be x plus delta x, which would be 2.5. And then y plus delta y, which would be 2 plus 1, which is 3. So do you see how my table kind of shows you where you're going and how you're using it? All right, well, we're not at 3.5 yet, right? Because that's what we're trying to approximate. So we're going to add, I'm going to take this point now and bring it over here. So this is 2.53, that's my new point. Delta x is not changing, it's 0.5. And now I'm going to find the slope at my new point, which is 2.5, that's right, which is whatever x is. And now I'm going to approximate the change in y by multiplying these two together, which is 25 times 5, which is 125, and the decimal moves 2 to the left, so it's 1.25. So my new point is going to be, I add 0.5 already to the x, which is 3, and then I'm going to add 1.25 to 3 and get, yeah, okay. I'm just making sure it's all over, right? So that's my new point, right? Am I at 3.5 yet? So I have to do another iteration. Delta x is still 0.5. And now I have to figure out what the slope is, and that's just 3, right? Because it's whatever x is. And then we multiply these two together to get the change in y approximation, which is 0.5. So I'm going to add 0.5 to the x, which gives me 3.5, and then 1.5 to the y and get 5.75. So we've reached now our destination, right, which was 3.5, 7.5. So I could say that my solution, f of 3.5, is approximately 5.75. Right? Now, part B says solve the IVP, and IVP stands for nothing but initial value problem. Right? So they're telling us to solve it. Now I gave you, I did a slope field here with all these solutions on it, but I'm going to talk about that in just a second here. Let's solve our initial value problem first. dy y dx equals x. To solve this and find the actual solution, the exact value, we're going to separate and integrate, right? So we get dy equals x dx. And we're going to integrate both sides, and we get y equals x squared over 2 plus c. And then they give us a solution. They said 2, 2 has to have to the point 2, 2. So using 2, 2, we can say that 2 has to equal, that's going to be 4 over 2, which is 2 plus c. So c equals 0. So then what is my solution? F of x equals x squared over 2. So f of 3.5. Can somebody please do that on the calculator for me? How close were we? I mean, 5.75, and we only took the answers of 0.5 away. So I took the liberty of doing a slope field here, so you can see what was going on. So we started at 2, 2, and then we went over, how far? 0.5, and so this is delta x, and then we estimated how high we were going to go, which was delta y, and created a new point, which was 2.5, I forget, 2.5, 3. Okay, and then I calculated a new slope based on the x value of 3 on that derivative, and then went over another delta y, or delta x, and then up the approximated delta y. So it's like I'm using multiple tangent lines, right? I'm creating a tangent line, even though the only one that's really tangent is the one that's first. And we just use the slope at this moment to help us generate the x and then the y up. And then we use the slope at this position, even though it's not on the curve, to go over and up. Because this slope is a nice approximation for what the rate of change is right there, isn't it? Even though that's not on the curve. This is an underestimation, clearly, because the curve is concave up. How do we know the curve is concave up? Second derivative, right? And what happens if we take the second derivative here? We get 1. And 1 is greater than 0, so the second derivative is always positive. Thus, the curve is always concave up. So you know that any estimation that you do using Euler's here will be an underestimation. Any questions? It's really not that difficult. It just takes some practice to do. All right. What I wanted to do for the rest of the time is I gave you a packet on the separation anxiety. No way. Right? And if you open that packet, you'll notice that I have taken the liberty of borrowing problems from AP exam, and as recent as last year, right? 2016, 2015, because last time somebody asked me, I don't remember who it was, pardon me for that, asked, am I going to have to create slope fields again? Okay, I know somebody there. You see how on the 2015, you're going to have to draw some slopes? That's how they're going to ask you. All right, so let's do the 2016 one together, if that's all right with you.
Oh, so it's not going to be like an entire graph, it'll just be a couple points.
No, I've seen at most 9. Okay, I've seen at most 9 points, I think. So let me put my problem up here. Now, it'll probably be this time, because I said at most 9, it'll be 10 or 11 or 12 points you have to draw the slopes for. But who's counting? Okay, so let me get this question here. All right. This is the last one I'll do with you. Now, this is a problem number 4, which means, only remember, 1 and 2 are the ones that are calculator active. So this is number 4, which means no calculator. See, I showed you how to do those lovely slope deals on your cool machine. Okay, so the first question, part A, says find the second derivative in terms of x and y. So for part A, dy dx is equal to x squared minus 1/2 y. So this is implicitly defined. How do I know that? There's a y on the right side. So the second derivative of this is going to be 2x minus 1/2 dy dx. Very nice. But do I know what dy dx is? No, I do. We do. We know that it is x squared minus 1/2 y. So we can plug that in here. So this will be 2x minus 1/2 x squared minus 1/2 y. Plugging that in. And so we get 2x minus 1/2 x squared plus 1/4 y. So this is the answer to part A. All right, so let's move on to part B. Part B says, let y equal f of x be the particular solution of the given differential equation whose graph passes through the point -2, 8. Does the graph have a relative minimum, a maximum, or neither at the point -2, 8? Okay, so first of all, in order to have a max or a min, does that have to be a critical point? How do we know it's a critical point? It makes the first derivative equal to 0, right? So that was equal to x squared minus 1/2 y. So what happens here? We get 4 minus 4, which is 0, right? Now I figure they made us solve for the second derivative to use the second derivative test here. What would the second derivative test tell us? The concavity, right? And if you find the concavity at a critical point, does it tell you whether it's a max or a min? So b squared y x squared equals, at this point it's going to be, this is 2x minus 1/2 x squared plus 1/4 y, such that x equals -2, y equals 8. So that's going to equal, I plug x in, that's -4, minus, it's 32? Oh, no, I'm sorry. I was plugging 8 in. No, I don't want to do that, right? Whew. Okay, minus 2. I was really jumping the gun, right? Plus 2. So that's equal to -4, which is less than 0. So what does that mean when the curve is less, got a curve that's less than 0? It's concave. It's concave down, and you are a critical point where it's the only place you can reside at a maximum, right? So we can say f of x has a maximum at x equals, or at the point, I should say, the point, -2, 8, since dy dx equals 0, and the second derivative equals to 0. Right? That's our justification, is the second derivative test. We have to do what's on top either side. If you do the first derivative, did we use the second derivative test? No. So that's nice. And I might even put it in here that you know that that's what you're doing, you know? I'd like a reader know that's the test you're using. All right, so part B. So it says G be the particular solution to the given differential equation with -1, 2 being the point. Find the limit. So what happens when we plug in -1 to this limit? G of -1 is 2. 2 minus 2 is 0. It's 0 over 0, isn't it? It's indeterminate. So we can't do that yet. Because I haven't introduced to you L'Hopital's rule. Have I? Well, I'm gonna foreshadow this a bit because I think that's the next section, right? L'Hopital's rule?
We might be the next two sections.
It's after, right. L'Hopital's rule says, listen to this, L'Hopital's rule says if you have an indeterminate limit, like a 0 over 0 or an infinity over infinity, because those can be indeterminate, then the limit will equal the derivative over the derivative. Then you can compare the rates of change. Yeah, I'll write it down. Hold on. I know I'm leaking. If the limit as x approaches a of f of x over g of x is equal to 0 over 0 or plus or minus infinity over plus or minus infinity, then the limit as x approaches a of f prime of x, oops, is equal to this one, it's the same limit. Their rates of change will be now I'll derive it in the next couple days. But so what we have is a 0 over 0 situation. So let's write our limit down. The limit as x approaches -1, and it was g of x minus 2, right? You have it on the paper. Over x plus 1 squared. Okay, so what is, this is 0 over 0, so it's indeterminate. So now I'm going to take the derivative. The limit as x goes to -1. What's the derivative of the top? G prime? Derivative of the bottom? 6. X plus 1. Now, let's see if we can do the limit. What's g prime of 1? Do we know? Oh, g prime is -1. Okay, so that means that g prime of -1 is going to be, what's the point at -1? -1, 2. So g prime is going to be 1 minus 1 minus 1, which is 0. So guess what? Is it indeterminate again? L'Hopital's going to rescue us one more time. So it's going to be the limit as x goes to -1 of, well, what is the derivative of g prime? G double prime of x over six. Yes,
That's a stupid question, but like, why don't you use like who time minus time to it?
because I'm not taking the derivative.
And,
I'm comparing the derivatives.
um,
I have two functions here, right, that I'm comparing. They're right, when I have a limit of two functions divided by each other, I am comparing their values as they get closer and closer to a certain number, right? So I'm not taking their derivative, right? But what L'Hopital says is that you can compare their derivatives, their rates of change as they get to that same location. And that'll be equal to the limit, which is really cool. And I'll show you another example in just a minute. But g double prime of -1, did we figure that out? G double prime, that's going to be at -1, 2. So g double prime is going to be the same thing here, isn't it? Yes. G double prime is going to be -2 minus 1/2. -2. I'm trusting you. So that's going to be equal to -2 over 6, which is -1/3. Okay? No, we're going to check the score guidelines. See, we're right. I know that this part you had to take with a little bit of faith here, but all right. What about part D? This is the drum roll right here, because this is what we learned about today, right? Let H be the particular solution to the differential equation with H of 2 equaling 0. Use Euler's method, starting at the point what? 0, 2 to approximate H of 1. Now they didn't tell us what the delta x is going to be, but they want us to take 2 steps to get from 0 to 1. So 0.5, right? Good. So we're going to do our chart, right? X, Y. The next one's going to be delta x. And then we're going to say the slope. And then we're going to estimate the rate of change of y by, or the change in y by the slope times delta x. And then we're going to end up with a point that's x plus delta x, y plus delta y. And we're starting at 0, 2. And my first movement is going to be 0.5 for the delta x. And my dy dx, I'm going to refresh my memory here, was x squared minus 1/2 y. All right. So dy dx here, using this point, is going to be -1. -1 times 0.5 is -0.5. So what's my new point? 0.5, comma, and then I add or subtract 0.5 from y, which I'm going to be at 1.5. Then I'm going to take that new point, bring it over here. My delta x is still 0.5. I'm going to figure out what the slope is at that point. That's going to be 1/4 minus 3/4, minus 2/4, which is -1/2. I'm going to say -0.5. Okay, and if I multiply those two together, I get -0.25, so that's a change in y. And so my new point's going to be 1. Now, why am I happy to see that? That's what we wanted. And then my new y is going to be this number minus 0.25. So this is 1.25. So I can say then with certainty, right? That f of 1 is, or h of 1, right? Because they wanted my function to be h. H of 1 is approximately 1.25, and did they ask us anything else? They didn't say it was an overestimation or anything like that, but we could have told them, right? We could have. All right, so the last thing I'm going to do with you is check the scoring guide to see how we did, okay? Here we go. All right, so you're going to have it open, right? Here we go. You ready? Let's see how we did. On number part A, if we got the derivative, we got how many points? 2. We got 2 points. The conclusion with the justification, we took the first derivative, found it was 0, that's a critical point, and we found out that -4 was negative, and so we know that it has to be a maximum. Using the second derivative test, 2 points. That's 4 out of 9. What do I want you to average? 6. So we're on our way. Now, L'Hopital's rule, so how many iterations did we have to do? We had to do 2, didn't we? Because we got 0 over 0 and 0 over 0. So you got a point for each iteration, and then you got 1 for the answer. So we got that right because I helped us through that, right? All right, and then the last one. Wait, is that right? Yes, right, because we said 1.25.
Yeah.
So we got a 9 out of 9. Woo! All right. So that's all I have for you today.